Welcome to another episode of Chemistry from Jay's House. Woohoo! This is the second solvation review video, so we're going to be reviewing more about solvation, which remember is nothing more than the nerdy term for dissolving. So we're going to be talking about dissolving some aspects of chemistry that relate to this. So one thing we're going to talk about is electronegativity. What that means and what differences in it cause, how that relates to things like chemical bonds, and more importantly, how that relates to things like polar molecules. Because polar molecules definitely play a huge role in dissolving or solvation. And while we're talking about this stuff, we also are going to get into hydrogen bonding, what that is, what the requirements for it are, and how that relates to dissolving, because that also plays a big role. And then when we've covered all that, we're then going to relate this all back to surface tension. What surface tension is, why water has enormous surface tension, and how these play a role in it, along with something called London dispersion forces. So we'll learn more about that in a moment. But first, let's talk about electronegativity. So we've already seen a couple videos about electronegativity. We've talked a lot about it. We've kind of used our Marvel Universe metaphor for it. Electronegativity is attraction. And it's specifically attraction of electrons. How much do electrons want to go to this atom? Now, here's the thing. It's not atom by atom in the sense of different atoms have different ones, because if we look at oxygen, it doesn't matter which oxygen atom I grab, they all have a 3.5 electronegativity. So it comes in families called elements. And that means that all oxygen atoms, and it doesn't matter if I'm getting it from air, if I'm pulling it off of water, if I'm pulling it off of sugar, doesn't matter, all oxygen atoms have a 3.5, which is different than sodium. So any sodium atom that I happen to see on the street would have a 0.7. And of course, hydrogen, same thing. Doesn't matter which hydrogen I take. I could grab it from the air, H2. I could grab it from water. I could grab it from fossil fuels. They all have a 2.1. So electronegativity is a single atom. What does this atom have? But it's defined by its element, what element it is. So thinking about that. And electronegativity, it's not just, we don't really care about how attractive it is in general. We care about it in relationship to other things. So we always talk about electronegativity in terms of difference. Again, I'm a hilarious guy. We all know that I'm, amazingly funny. But if you put me in a room full of professional comedians, I'm not funny at all. They will destroy me. I'm just a moderately humorous human. You put me in a room full of, actuaries and accountants, I'm going to kill. I will be king of comedy. So it's all about difference. Oxygen has a high electronegativity, but the difference between oxygen and oxygen, if I were to subtract these, is, 0. And that means that an electron wouldn't know which way to go. Does the electron go to this oxygen or that oxygen? Doesn't matter, because it has 0 difference. So we're not talking about this in a vacuum. We're talking about this in relationship to another atom. So if we look at, let's say, oxygen and hydrogen, now we have to pull out our calculators, do a little bit of math, and we get 1.4. And that means that if an electron is walking down the street and has to choose between these two, it'll choose oxygen most of the time. 1.4. That is 1.4 more attractive than hydrogen. It will occasionally choose hydrogen, but probably not for long, not for long stretches of time at least. And what about oxygen and sodium? Well, if we do a little math here, we find out, oh my gosh, it's 2.8. Whoa, that's enormous. That is a huge difference. That means that pretty much every single electron is going to go to oxygen and spend no time here. But there's other differences, such as, well, what about hydrogen and sodium? And it turns out that hydrogen and sodium is also 1.4. So that means if I were to look at oxygen and hydrogen, so if an electron is walking down the street, right? And this electron it has to decide between hydrogen and sodium. 1.4, its desire to go to hydrogen over sodium is 1.4. It's the difference, it's the change, which is the exact same amount of struggle that this electron has between oxygen and hydrogen. Again, it's the difference. It's how hard of a decision is this going to be. For orange, it'll be 1.4. It'll be drawn 1.4 electronegativity difference towards hydrogen, which is the exact same amount of draw of oxygen away from hydrogen. So even though this one chooses hydrogen, this one doesn't. With the same strength, because again, it's not in a vacuum, it is the difference. That's what we're talking about with electronegativity. I don't care what the electronegativity of a single atom is. You have to give me a pair for me to care. Let's get rid of all that noise and nonsense. So electronegativity, the differences in them give us different behaviors. So looking at this again, if there is a huge difference, and that means it is greater than 1.7, and that would be something like, oh, well, we have oxygen minus sodium, and that's a difference of 2.8. What that means is that all of the electrons are going to go to oxygen, all the free electrons, any single electron comes down, it's going to go oxygen, and oxygen will take on a full-time negative charge. And that will leave sodium with a positive charge. Now what that means is, in this particular case, sodium, and you'd have to look at your periodic table, has one electron it doesn't want. So it will send one of its electrons over to oxygen. Why? Because oxygen is 2.8 more attractive. Look at that, 3.5 versus 0.7. Oh my gosh. So as one electron leaves sodium, goes to oxygen, it's going to stay there. It's never going back. I finally got out of that terrible situation with sodium, and now I'm in a much better place, and I am going to stay here. So those are full-time -1 charge, full-time +1 charge, and I don't write the 1 because scientists are lazy. And this is what we call an ionic bond. Now, what if there is like the three little bears, a medium difference? Let's say it's between 0.4 and 1.7. And we happen to have an example of that. That would be oxygen and hydrogen. And doing the math, I get 1.4. And what that means is that electrons are going to be more drawn to oxygen, but they are going to occasionally come back to hydrogen too. The difference is medium amount. Any free electrons will spend more time with oxygen. There's definitely going to be more time here, but there is a cycle back to hydrogen too. And what that means is at times oxygen will have more electrons, but at times hydrogen might even have more electrons, or they might have equal number in terms of number of electrons versus their protons. And what that means is this is kind of a negative, this is kind of positive, but not all the time. If I were to have a strobe light flashing on this relationship, most of the time there'd be more electrons around oxygen. But occasionally there would be a couple flashes where it's actually balanced out. And there might even be one flash where hydrogen actually has more electrons because this just happened on a fluke. So these charges are, this is most of the time going to have a slightly negative lilt to it. This will have a slightly positive lilt, but it's not like here where this is a one-way street, never to return. There is a cycle here, and that means that it's covalent, but because it has a negative pole and a positive pole, it is polar covalent. And then what if it has just a middling, a small amount, a small difference? And that is, what if it is less than 0.4 difference? Well, less than 0.4 difference is the same, acts the same pretty much as no difference. So that could be even something like sodium versus sodium. Wait, Jay, they both have really low electronegativity. That's a really bad example. Actually, it's a brilliant example because it's the difference. I don't care about the absolute electronegativity here. I care about the difference. And what that means is sodium to sodium has a 0 difference in electronegativity. That means that an electron coming in doesn't matter. It doesn't care where it goes. So there's not going to be a draw to one side or the other. And that means this example does not change at all if I swap out sodiums with hydrogens. It's still 0 and 0. Electrons still are going to spend equal time around both. And it doesn't matter if I flip it with oxygen and oxygen. Again, the difference, it's the difference that defines it, not the atoms themselves. And since it doesn't have a positive or negative pole, it is a nonpolar covalent bond. And just to really nail this down, that means if I take oxygen and hydrogen, now remember, in this situation, hydrogen is slightly positive, but what if I pair that up against sodium? Now the math happens to work out that it's still a 1.4 difference in their electronegativities. And now hydrogen is going to be the negative pole of this polar molecule because, well, it's 1.4 better than sodium. But now, instead of things leaving sodium, like up in the ionic, they will occasionally circle back around. Electrons will come back to sodium because the difference isn't that great. And to see it in movies, again, doesn't matter which I choose down here. Fantastic Four minus Fantastic Four gives you 0. That's going to be nonpolar. And we could even do, Fantastic Four versus Iron Man 2. Oh my gosh, look at that. Again, there's going to be a 1.4 difference between these, so that's going to be, it's going to spend more time around the Iron Man 2. And oxygen and Fantastic Four, there's a huge difference in the likability of those movies. So you're definitely going to have ionic. There's going to be stealing. There are electrons that are going to leave Fantastic Four, go to Avengers, and never come back. So that is electronegativity. And it all kind of fit on the screen. That's nice. So let's keep moving. We got things to review. So that's the electronegativity review. I've talked about it in a couple videos. There's also tons of videos in the internet that will explain it, so feel free to search for other people's words as well. Now, I want to talk about hydrogen bonding. So hydrogen bonding is just another bond that happens between molecules. It is an intermolecular force. So when we were talking about ionic bonds, and we were talking about polar covalent bonds, and we were talking about non-polar covalent bonds, those are inside of a molecule. That would be an intramolecular force, if that were a word, right? This is an inter. And inter means between, right? International flights go between countries or in between nations, international, right? The internet is a network between computers, right? Inter means between. So now we're not talking about holding atoms together. What we're talking about now is holding molecules together. That's a pretty big thing. Now we're talking about molecules being stuck together. It's not a single oxygen and a single sodium. Nope, not that at all. Now it is a water molecule held together by polar covalent bonds and a water molecule held together by polar covalent bonds. And then the intermolecular force is the force between these molecules. So just be clear, we're not talking about these forces between oxygen and hydrogen. We're not talking about these forces between oxygen and hydrogen. We're talking about this water molecule and that water molecule and what holds them together. So we're switching from the atomic view to the molecular view. And the one that we care about, the one that we're going to talk about right now, is called hydrogen bonding. Now, hydrogen bonding is nice in the sense that it's just a checklist. You just need two things. One thing you need is, well, hydrogen. No way! They should have called it hydrogen bonding. And the second thing you need is an electronegative atom. So remember we were talking about electronegativity? That means an atom with a high electronegativity. So 2 is ding! Something with a high electronegativity. So the way that works is, remember the hydrogen has to be on one molecule and the electronegative atom has to be on a different molecule. This isn't inside water. This is between waters. So one water here has the hydrogen, one water here has the oxygen, and then what we're talking about is this right here. That is a hydrogen bond. And the reason why is because oxygen, with its high electronegativity, 3.5, the highest value is 4, oxygen with its high electronegativity is, well, electronegative. Electrons really want to spend time with it. And hydrogen, with its relatively lower electronegativity, it's only at 2.1, ends up getting attracted because it ends up being kind of positive. So hydrogen bonding has a lot to do with magnetism. You'll notice magnetism coming up a lot in all areas of chemistry. Magnets are kind of rule or reign supreme down at the atomic level. So what you need for a hydrogen bond is simply one molecule has to have hydrogen, a separate molecule has to have an electronegative atom, and bing, there it is. You get a hydrogen bond. And what that means is, if we look at a couple water molecules, and let's say that we're looking at a droplet of water here, and we got some water molecules like that, and it's liquid water, so it's able to kind of slosh around and move all over the place, right? These water molecules are going to go absolutely everywhere, and they're going to slosh around and have a grand old time. Now, why doesn't this water molecule shoot off and say, see ya, I'm going to go try my wares in LA and become world famous? And the reason why is because it's getting sucked back in by intermolecular forces. This is one molecule getting sucked back into all the other molecules by intermolecular forces. And one of those forces is this hydrogen is getting attracted back to the oxygen that's still in our puddle. And what can happen is these can switch. Whoa, now you're attracted to me. Whoa, now you're attracted to me. Whoa, now you're attracted to me. But regardless, I can't get away and live my dream. Nope, you can't. Come back to the herd. And that's how water stays as a droplet. That's why it takes on like circular forms when it falls from the sky and that sort of stuff, because it has hydrogen bonding. Again, you only need two things. you need hydrogen on one molecule, and you need oxygen with its high electronegativity, bing, and then between them will form a hydrogen bond. Okay, and the final thing we have to talk about is surface tension. Surface tension has a lot to do with water, so we'll leave those out. Now, again, surface tension is an intermolecular force. Surface tension is the ability for water on the surface to really care about the water and hold on for dear life with the other water at the surface. Underneath the surface, woohoo, woohoo, you have water everywhere. Underneath the surface, water can do whatever it wants. And it's key to remember that under the surface, as these things are all moving around, that it should be a 3D model, which means water should be coming up off the board, right? Water should be actually diving through the board and going underneath, right? This is a 3D, it should be a 3D model with water going up and in and going all over the place. But that's a different thing at the surface. Because here, this water molecule can technically go anywhere. It's inside the water. But up here, when it gets near the air, the water can't, woohoo, run away. Why not? Well, there are 3 reasons. Because there are 3 things holding this guy down. I know he's a dreamer. He wants to go out there and be world famous, but you can't. You must get dragged back away from your dreams and live in the small town called this puddle for the rest of your life, water. And there's 3 reasons why. One we just talked about. Hydrogen bonding. As this guy tries to get out of here, woohoo, I'm out of here. Water at the surface goes, oh really? Well, I know you have a hydrogen atom and I have an electronegative atom, so hey, there's a hydrogen bond happening between us. And that hydrogen bond doesn't exist with air, because air, again, air doesn't have these large differences in electronegativity. So we have hydrogen and we have oxygen, and so one of the bonds that happens here is the hydrogen bond. Now technically water does hydrogen bond with air because it does have O2, but I want to focus on this and this now. So one bond between these is that. Now note, if these rotate, you still have a hydrogen bond, except this time this molecule is offering its hydrogen, this molecule is offering its oxygen, and if it rotates again, oh my gosh, you still have a hydrogen bond. Now this time this molecule is offering the hydrogen, this one is offering the oxygen. So as you might guess, these hydrogen bonds, as these floating around, are coming into existence and snapping out of existence often, right? But I said there are 3 reasons. That's just one reason that this water molecule can't go live its dream. And the second one is, wait, didn't we say that it's a polar molecule too? Which means, hey, these little positives and negatives. Not only does hydrogen want to hang out with this oxygen, but it's also positively charged, and this is negatively charged. That means there is a second bond here. It is a polar molecule, which means it's just positives and negatives. It's just magnetism. It's just a cute way of saying magnets. So not only is hydrogen bonding holding this hydrogen to that oxygen, magnetism is holding this hydrogen and that oxygen because it's a polar molecule, because of the difference between the electronegativity of this oxygen and the electronegativity of this hydrogen, and that difference means that, yep, electrons are going to spend more time here, less time there, same thing here, so you end up getting relatively positive and relatively negative ends. Okay, and what about that third one? You mentioned London dispersion forces. Oh, did I? I'm so sorry, I wasn't supposed to say that yet. London dispersion forces. It's a type of van der Waal bond. Van der Waal bonds are like the general terms. But London dispersion forces kind of exist everywhere. They exist between all stiff. And that has to do with electron placement. Because these electrons are zipping around all the time, if you were to take, high-speed photos, snap, 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 and check out where the electrons are, there are times they're going to be a little more at the top of the molecule, or more at the bottom of the molecule, or more at the right, or more at the left, which means technically every molecule is going to end up having these kind of being instantaneously polar in some realm. All right, so one end is going to become slightly negative, then become slightly positive as electrons are zipping around without any rhyme or reason. So simply because it exists, and we find London dispersion forces with everything that exists. So these are not unique. There's nothing really unique about London dispersion forces. All molecules experience them, but it is a third force. So what's unique about water is not only is water a polar molecule, it also engages in hydrogen bonding because it has a hydrogen and it has a oxygen. So you have three forces holding all these together. And there's no way this guy's going to get away, so he gets sucked back down into the group. Now, these three forces are happening between all of these molecules in the solution. So in the water, all right, these guys, as they move around, hydrogen bonds, polar molecules, London dispersion forces. Polar molecules really just means magnetism, right? Right? They're snapping into existence and snapping apart, and they're constantly, as these two pass, some of these things will form, and they might rotate to kind of deal with it, and then they might fly on and they go. So these three forces are constantly happening, but they're happening at all 360 degrees down here in solution. So down here, it's going to be hydrogen bonding with ones, this water molecules hydrogen bonding with these. But it's also hydrogen bonding with this and with that. And it's also hydrogen bonding with ones above it and one below it. And so it's bonding with atoms in all 360 degrees. But that's not true up here. Up here, this guy's kind of bonding this way, and that guy's probably bonding that way, and this guy might be bonding kind of this way, and this guy might be bonding a little bit that. But here's the thing. They're not bonding up. So where this, if we look at, let's say, this one particular water molecule, right, you're going to find, between it, you're going to find polar bonds, polar bonds, polar bonds, which is really just magnetism. And you're going to find hydrogen bonds, hydrogen bonds, hydrogen bonds, right? You're going to find London dispersion forces, London dispersion forces, London dispersion forces. But you're also going to find it up here. What about these molecules up here? Oh, yeah, well, you're definitely going to have all three, right, happening there too. So you're going to get them, poorly drawn, all three, poorly drawn, all three, right? And so that's going to happen 360 degrees. It's also happening up. It's happening down. It's all the way around. But what about these guys? Here's the thing. You're going to find those between them. So let's just look at these three water molecules here. You're going to find London dispersion forces between them. But can they do London dispersion forces with air? No, not really. So the London dispersion forces that would be going up come sideways too. So the London dispersion forces that would go up come sideways too. Now, it's totally going to bond to ones underneath it. But that's only a single. Here, you're getting doubles and triples, because where it would go up, now those London dispersion forces double down to the closest water nearby. And you'll see that with polar molecules. It will bond polar, magnetism below, magnetism beside. And it would do magnetism up, but there's nothing up. So then we get additional forces on the side. additional magnetism because it's a polar molecule on the side. What about hydrogen bonding? Same thing. It's going to hydrogen bond with atoms below it. It's going to hydrogen bond with atoms beside it, but it can't hydrogen bond with anything above it, so they double down. You're going to get additional hydrogen bonds to the side. And now if we look at it, in solution, you kind of have singles all the way around. These are poorly drawn. I should really redraw these. Man, you guys have a lazy chemistry teacher. Don't tell him, though. It's a good way to fail his class. Just kidding. So in solution, you would have single hydrogen bonds, single London dispersion forces, single polar molecule, aka magnetism, all the way around. But near the surface, you're going to get singles on the way down. But what about at the surface? Look at all that. Look at all those additional forces. It's those additional forces that only happen at the top, because where these forces would like to go is they would like to go up. They'd like to be, like this one, single bonds all the way around, but there's nothing up there. There's no water up there. So all those additional forces, they don't disappear, they still exist, they just have to go to the closest handhold. And the closest handhold is beside it. So what that means is, because you have hydrogen bonding, water is a polar molecule and engages in magnetism, and London dispersion forces, which everything does, you're going to have huge surface tension. At the surface, you're going to have all those additional forces that would go up, go to the side. So they double down or they triple down sideways, and that's why water has huge surface tension, because it engages in 3 intermolecular bonds. It bonds with other water molecules 3 different ways, where most molecules only bond 1 or 2 different ways. Water triples down, gets all 3. And so at the top, it's not a single bond kind of doubling down, but it's 3 bonds doubling down. So you get more and more tension at the surface. That's the whole dog and pony show. I hope you guys enjoyed it. I know it's mind-blowing and amazing. Feel free to send Oscars or Emmys or money as a way to thank me. Good luck.